Okay, so let's continue the lectures. So yesterday we saw a result, and in some sense formally this is this result that tells us, okay, if I have some surface sigma in my ambient manifold, I can try to look at, minimize the area among all surfaces that are in the isotopic class of sigma and find something, which is area minimizing, so minimal. But the question at the beginning is, okay, you need to know that in some sense the surface is incompressible. So it does not have to disappear when you do the minimization. So this is, in some sense, yesterday's theorem tells this. Okay, so it has its own interest, and you can find a lot of minimal surfaces like this. But there is some manifolds where you can't apply this. For example, think about M3, which is just the 3 sphere with some metric. Any embedded closed surface inside this is compressible, so everything disappears. So you can try to apply this, but at the end what you find is that the least area is just 0, so there is no surface at the end. Yes?
In the relative case.
What do you mean?
If the surface has boundary, it may be.
Ah, yes. If the surface has some boundary, yes, you can apply exactly the Douglas and Rado theorem in S3. There's no problem. But here I'm looking for closed surface without boundary. And okay, so this is the problem, and how you find minimal surface, so closed minimal surface inside such a manifold. Is it possible to prove that there exists some there? And the answer is yes, you can prove this, and it's the main topic of today, which is existence result 2, so the second part of the existence theory. And before looking at surfaces, let me think about what is the problem. The problem is to construct a critical point for some functional. So the basic idea is, okay, you can do minimization. And here I say minimization is not a good idea because everything are going to disappear, and so the only minimum is 0, nothing. So maybe you can apply some other idea to construct critical point, which is Morse theory. So the idea is to apply some Morse theory. And the picture is the following one. So imagine that your space of surfaces, say, is like this. So it's a big torus in very, very high dimension. So this is the space of surfaces in N. And here you put the area functional. So in some sense, the vertical direction is just the area functional. So here, at that point, what is this? It's just the point where the area is equal to 0. So in some sense, it's a surface which is either empty or reduced to a point. So you see nothing. And it's the absolute minimum for the area functional. Okay. But what you see there is that there is some critical point for the area functional there. And how you capture this critical point? So the idea of the Morse theory is, okay, you look at a path there that come back on the other side, and you look at the maximum point along this curve. So there, so you get some value for the area, which is the maximal area along that path of surfaces in your big ambient space of all the surfaces in M. And in order to see exactly what is the value of this, what is this singular value for the area functional, the idea is, okay, now look at all these paths that are homotopic to this one, look at this quantity, and try to minimize it. So the idea is that when you do this, you construct some other path inside your space of all the surfaces in M, and at the end, maybe by chance, you will reach precisely that point, and you get some critical point for the area functional. So maybe it's possible to do this to construct some minimal surface inside my sphere with some metric on it. And in fact, this idea works first, and it goes back to an idea of Birkhoff. Birkhoff. And about what problem Birkhoff enter into the game, because of for the problem existence of closed geodesic on a Riemannian two-sphere. So the question was, okay, you look at a two-sphere with some Riemannian metric, like this, and you want to construct some geodesic, closed geodesic on it. So what is the idea of Birkhoff? The idea is the following. So you look at gamma sub t, so a family, t between 0 and 1. So what is this? It's a continuous family of closed curve on S2, so on this sphere, so say on S. Okay, and such that gamma naught and gamma 1 are just 1 point, are constant. Okay, so the picture is the following, in fact. So here I have my interval 0, 1, and here I have just the unit circle. And it gives me a parametrization of this family of continuous closed curve. So if I use some color, maybe here I look at this, and here I have some curve which is parameterized exactly by this one, and this is, say, gamma sub t for some t. And one assumption I put there is that, okay, I don't know if the green is okay in this picture. This curve is sent only to 1 point somewhere in the surface, and this one is also sent to some point somewhere into the surface. Okay? So there is a kind of map F which sends the cylinder to the sphere which is continuous and which has this property to be constant there and constant there. So because of this, in fact, the space of parameter, you can collapse this S1 to 1 point, this S1 to 1 point, and in fact what you can see is just a map from the sphere. Here I have my blue circle there, and F map in fact the sphere to this Riemannian sphere in a continuous way. Okay. So we keep this picture. Okay. And so Birkhoff says, okay, we say that such a gamma t, so such a family, is a sweep out if the map F has degree equal to 1. So it's a continuous map from the sphere to the sphere, so it has some degree. And you say that this is a sweep out, this continuous family of curve, if the degree of F is equal to 1. Okay. Okay, and now you define some quantity, which is just L. You look on this family gamma sub t to the curve which has the maximal length. So you look at the sup of the length of gamma sub t. And on my picture, which is there, gamma sub t, what it is just a continuous path in the space of all curves on the sphere, so like this, and I look at the maximal point for the length functional. And if I want to apply this Morse theory idea, I have to minimize among all the paths that are homotopic to this one I have fixed. So the idea is that I take the infimum now among all sweep out. And the idea of Birkhoff is that, okay, this number has to be the length of some closed geodesic on S2. And in fact, he proved this. The thing is that first, because the degree of F is not equal to 0, here, this hypothesis, you can prove that L is positive. So you think a bit about this. If all the curves are short, for example, say less than the injectivity radius, the injectivity radius of this Riemannian surface, then you can contract inside a geodesic disk all these curves to one point. Then after you just in this space there, the sweep out you get, you can contract each curve to one point, and so the length is equal to 0. But if you are able to do this, it implies that the degree of the map is not equal to 1, it's in fact 0. So you have this for sure. And so the idea now is to apply some min-max arguments to prove that in fact you really have such a geodesic. So what is the idea of Birkhoff? It's based on the curve shortening flow, curve shortening discrete flow, which is the following. Okay, you take a curve like this, and you look at the parametrization of it by arc length. And you cut this parameter space into equal length sector or interval, like this. And you put an even number of points there. And so the idea now is you look at all the points there that are the image of 1 over 2 of all this point there. This one, this one, this one, this one. Okay, I have some mistake there. So I need one extra point there. So it gives you some points. And there. And you say, okay, one thing that I can do is to replace that curve by a curve which is made only by geodesic arcs. And so what I do is the following thing. I replace this curve by this one. So you have to imagine that this curve is in fact on the sphere which is there, this Riemannian sphere. And you can do this if the number of points there is sufficiently high. Then the second step is okay, because there is all these points where we have done nothing. You look at the midpoint of all these geodesic there. And you redo the exchange. You change this by the geodesic from there to there, 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 and there. So starting from one curve, you can replace it by this new curve, which is this curve made by geodesic segments like this. So what is the interest of this? So this map, this transformation, I call it D. Say. So what is the interest of this? First, D of gamma, if gamma is this curve, is homotopic to gamma. And this is true if you choose the number of points there sufficiently large. The second point is that, okay, if you look at the length of D of gamma, it's less than the length of gamma. Because at each time you replace a curve by a geodesic, a shortest geodesic between 2 points. So this geodesic has length less than this one, and this geodesic has length less than this curve there. Okay. And moreover, the thing is that if the length, it's the length there. If the length of D of gamma is equal to the length of gamma, what you can see is that in fact gamma is a closed geodesic. And it's in order to have this last property that you have to do this change twice. Looking at first, you exchange by some curve which is made of geodesic arc, then you look at the midpoint and you do it again. It's because you want this property to occur, to happen. Okay. Closed, smooth geodesic. Okay. So now you look at this problem there. And you look at gamma I, T, or T in 0, 1, a minimizing sequence. Okay? And you look, in fact, also to this quantity, to this new family, which is you just replace the family by the image by this transformation there, by D. The thing is that, okay, first you prove that because of this, this new family is still a sweep out. The fact that you have some homotopy between each curve implies that, in fact, you have an homotopy between all the map there. And so the degree of the map F that appear for this new family of curves is also 1. So this is a sweep out. And because of this, the sum of the length of this for I fixed and T moving from 0 to 1 is less than the sum of this for the same I. This is a minimizing sequence, so it's also a minimizing sequence. Okay. So now we can choose some Ti. We choose Ti to be such that d of gamma I Ti has length going to L. So in some sense, you look at the T such the length of this curve is of these curves is maximal, and because it's a minimizing sequence, the length of this precise curve has to go to the value L I defined there. Okay. And you can also notice. Sorry.
You assume that gamma IT is the maximum of the sweep out.
Yeah, I choose Ti such that this curve there has the maximal length in this sweep out. In some sense, okay, I choose the point which is the highest on this picture. Okay, and one thing that you can notice also is that the length of gamma I Ti also goes to L, because this length is larger than this one, and it's less than something that goes to L, because it's a minimizing sequence. So you also have this. Okay. One thing that you can also assume, now you can assume that gamma I Ti and d of gamma I Ti converges to some curve gamma, and in fact the map D you can prove it's continuous. So d of gamma I Ti converges to d of gamma. So a priori you need some regularity issue to prove that such a sequence of gamma I Ti converges to something. The idea is that in fact you apply d one first time. So you replace all the curves in this by curves made by geodesic segments. And curves made only by a finite number of geodesic segments, it's in some sense it's compact. It's a finite dimensional space, so and it's compact, so you can extract. So you apply d once, then you reapply d a second time, and so in fact you don't work with this, you work with the image of this by d, and the image of this by d square. But you can assume this for that.
As you start with arc length parameterization,
Yes.
it will be continuous. So you can apply that.
Yes, but the thing is that, yeah, you can apply Ascoli, but the thing is that at once in the really in the argument you have to change a bit the parameterization, and you lose this aspect of the proof. When I say that I start with the arc length parameterization there, it's in order to make this construction. But it's not clear at all that you can have a continuous family parameterized by arc length and things like this. It's a bit a difficulty in the proof, but it's not so hard. But in fact, if you want to prove all of this, you have to take care about the parameterization, and it's a bit a problem. But the idea, the main idea is that in fact you work with curves made by a finite number of geodesic arcs, and it's a compact this. Okay. Okay, so you have a curve gamma, you have this there, and moreover you have the length of gamma is equal to L, and it's also equal to the length of d of gamma. Okay. So the thing is that you apply this characterization that tells you, okay, gamma is a closed, smooth geodesic on the surface. Why this?
Gamma and d of gamma are the same. You claim that both converge to the same curve?
No. I say that gamma I Ti converge to some curve gamma. This converges to the image of gamma by d, because d is continuous. And moreover, the length of this sequence and the length of this sequence goes to L. Okay? And the length is continuous also. So you have this. And so by the characterization which is there, you prove that gamma is a closed geodesic. And you have proved that there is a closed geodesic on the surface on your Riemannian sphere. Okay. So now the idea is, okay, let's do the same for surfaces in some three manifolds and try to obtain something. Okay. So mainly I will not enter into the idea of the proof, but I will say something about some of the difficulties. And I will state mainly one theorem. But the basic idea is exactly the same as the one of Birkhoff. So this is the second step. So min-max theory to produce minimal surface. Okay. So this idea to construct some more theory on the space of surfaces inside some manifold goes back to the end of the 60s, all the 70s, and the beginning of the 80s. And there is also some recent development on this. And in some sense, the two major guy in this problem is Almgren and Pitts. So I won't state the theory of Almgren and Pitts, and I will state another theory, which is in some sense a simplification of the theory of Almgren and Pitts, but it's sufficient for what I want to say today. So you have these two guys. You have also the work of Smith, more or less at the same time, and Simon, which improve a bit the theory of Almgren and Pitts in order to construct spheres, two-dimensional spheres into three-dimensional spheres, which are minimal. There is the work of Schoen and Simon, which is more about the regularity theory of the theory of Pitts. But for today's talk, since I focus on surfaces, everything is already in the result of Pitts. And you have some other version, so due to Kolding and Delelis, which is more recent. And in fact, the theory I will present today is very close to the one developed by Kolding and Delelis. And in fact, it's due. So the statement I will give appear in a paper by Delelis and Tasnadi. So I really want to give something which is true, a true definition and a true theorem. It's not exactly what appears in the work of Almgren and Pitts, but it's sufficient for today. So what is the statement and what is the idea? So the thing is that, okay, we have this space of surfaces and we want to look at continuous curve in the space of surfaces. So we have to define what is the continuity in the space of surfaces. So Delelis and Tasnadi, they define the following thing. Definition. So a family gamma sub t for t in a cube of dimension k. And I will use this only for k equal to 1 and 2 of closed subsets of M. So M here is just a closed three manifold. and you assume also orientable. So you look at a family of closed subsets of M, but in fact you will see that they are much more than just closed subsets. You assume with Hausdorff measure of dimension 2 finite with finite. So you say that this is a generalized family if so you need some property in order to say, okay, they are continuous in the parameter t, and they are surfaces. So what do you want first? For any t, you ask to have some subset of M, which is finite. So this is just a finite number of points, such that gamma sub t is a smooth surface outside Pt. So when you look at gamma sub t outside some point in your manifold, you have a nice surface.
Do you need the two-dimensional is the bounded?
Sorry?
Do you need the family's measure is the bounded?
I'm not so sure to understand the question. In fact,
You need you say the Hausdorff.
the Hausdorff measure is finite for any t. For any t, the measure is finite. But I will ask something more after. In some sense, it appears there. So if you look at H2 of gamma t, so precisely the Hausdorff measure of gamma sub t, is continuous in t. And if you look at the map t goes to gamma sub t, is continuous in the Hausdorff sense. Okay, so as a family of closed subset, it's continuous in the Hausdorff sense, and moreover, you want to be sure that the Hausdorff measure of gamma sub t is continuous in T. So since we are on a compact subset, we have an upper bound for the whole family. Okay, and the last point you ask to have a continuous family is the following. On any open subset included in MT minus PT. So you look outside of the point PT and you look into some subdomain of this. Then gamma sub T, gamma sub S goes to gamma sub T when S goes to T. So here I assume something about the convergence of gamma S to gamma sub T in the Hausdorff sense, and here I want something more. I want this smooth convergence, smoothly. What I mean by smoothly is just that I want that for S very close to T and inside U, gamma sub S is a graph, can be described as a graph over gamma sub T. And this graph is given by some smooth function, and when S goes to T, this smooth function goes to 0 smoothly.
No continuity of this.
PT, no. Okay. In general, what happens is that PT is empty for almost every T, and for some T, there is some point to remove. The thing is that the idea is that these point PT are just there in order to allow you to change the topology of the surface gamma sub t. Sorry? Yes, for example. You can think about the following picture, and I will give you, in fact, an example just after of this. Okay. So this is just a notion of continuity in the space of surfaces inside M. So now I want to speak about what is a sweep out. Okay? So what is a sweep out? And the idea is, okay, it has to be in some sense a continuous family of surfaces, but I have to assume something which was just before, the degree of the map has to be non-zero. So I have to explain what is this idea there. So the idea is that, okay, gamma sub t, and now it's just for t between 0 and 1, is a sweep out. If it is a generalized family, so in the preceding sense, and there is a family omega sub t for t between 0 and 1 of open subsets in M such that first, if you look at gamma sub t, so it's a closed subset, you remove from this the boundary of omega sub t, and what you want is just that this subset, this closed subset, is inside P of t. So in some sense, gamma sub t is just the boundary of omega sub t. But sometimes you have to add some point somewhere in the picture, so you have some trouble with this, so you put this. The second thing is that omega naught is just the empty set. And omega 1 is the whole manifold. So it implies that gamma naught, because of this, is just a finite number of points, maybe the empty set. And gamma 1 is also a finite number of points, maybe the empty set. So its H2 measure is 0 for both. So in some sense, you start from a surface of 0 measure, so 0 area, and you go back to a surface with 0 area. So you have a loop in the space of surface, yes, starting from the absolute minimum of the area functional and goes back. Yes?
Passing to that definition,
Yeah.
there needs to have some sweep out on, for example, Haken manifold which are nocturnal.
You will see the example just after, and you will see that for any closed manifold, there is no problem with this definition. But just wait, I finish the definition and give the example. And the last point you need also, and it's in some sense, it's a straightening of the continuity there, is that if you look to the symmetric difference between omega s and omega t, this goes to 0 when t goes to s. So it's a kind of continuity issue for the family omega sub t. Okay. So now the example, and I will discuss all of this just after. So what is the example? So you take f from M to R a Morse function. And the thing you do is the following thing, not from 0 to, but from 0 to 1. So you have your surface there, your manifold M there, maybe with some topology somewhere. And you look at gamma sub t is just the level set of the Morse function. So the thing is that maybe if you are at if t is a regular value of the Morse function, there is no problem. You have a smooth surface, gamma sub t, which is well defined. But maybe sometimes you reach a point which is a singular value of this, of the Morse function f. And here you have something which is not anymore a smooth surface, except, and in fact it's a smooth surface except at that point which is there. So you have to put that point in the subset Pt. So the example. You look at the Morse function on your manifold M. And you look at the level sets of this Morse function. So you see that all this works for that kind of example. And the thing is that what is omega sub t is just the sublevel of f. And it's true that if you start for t is equal to 0, you have the empty set. For t is equal to 1, we have the whole manifold. This is also true, no problem. And this is also exactly the thing. In fact, in that case, you have equality, and maybe except when you are there, where there is only one point. That's not exactly the case, but it's inside the set of points you have to add to your manifold, to gamma sub t. And you see in this picture that the point Pt are really there when you change the topology of the level set. So they are used only in that case. Here I have also some picture there. And here I have to add some point in my set P sub t for that value of t. Okay. So now, okay, but maybe I can do exactly the same and put there the empty set also, and not M. The thing is that if I put there M and not the empty set, is to be sure that the path I describe in the space of the whole surfaces is not contractible. And this is this that replaces the fact that the degree of the map has to be 1. It's exactly this. Okay, so we have this long definition. And now the thing is that you apply the idea of the Morse theory. So first, the first proposition is just, okay, you define f of this sweep out, or t between 0 and 1, to be the max of the Hausdorff measure of gamma sub t for t between 0 and 1. Okay, so this is the leaf in my sweep out which has maximal area. It's the value of the maximal area of all leaves. And the first thing is that you have the following proposition. There is a constant Cm, which is positive, such that this value, so this quantity, t between 0 and 1, is at least C of m for any sweep out. why this is true. In fact, here I can make a proof of this. You look at the hypothesis you have on omega sub t there. So the volume of omega sub t is continuous. And it starts from 0 and goes to the volume of the whole manifold. So there is t such that the volume of omega sub t is equal to 1/2 the volume of the whole manifold. Okay? And now what you can see is that in fact, so the measure of gamma sub t for that particular value of t is just the measure of the boundary of omega sub t. But this is exactly what you are looking at when you look at the isoperimetry of your manifold. It's larger than the isoperimetric profile computed at volume of m divided by 2. And this is positive. Okay. So you have this. Okay, so now one thing that you can also define is that you say that if gamma 1 t and gamma 2 t are two sweepouts, then they are homotopic if there is a generalized family gamma ts in 0, 1 square such that, so you ask that gamma sub t 0, 1, sorry, here it's 0 and 1. So gamma t0 is equal to gamma t0 like this, and gamma t1 is equal to gamma t1, and gamma ts, if you fix s and let t between 0 and 1, what you want is that this is also a sweep out. So they are homotopic if there is a continuous path in the space of all sweep outs from one to the other one. Okay, and if gamma t naught is a sweep out, you define let capital lambda be its homotopy class. So you look at, you have a loop in your space of surfaces. You look at the homotopy class of this loop. And you define, as Birkhoff and as the idea of the Morse theory, W of m to be W of capital lambda, the infimum among all sweep outs in lambda of the area the largest area of leaves in the sweep out. So you have a loop, you look at the maximal value along this loop, and you minimize among all the loops in the homotopy class. Okay. So the idea of the Morse theory is that, okay, first, because of the proposition, this is larger than C of M, so it's positive. And the idea of the Morse theory is, okay, this is a singular value of the area functional. So there is somewhere a minimal surface which has area exactly this quantity. So you produce a minimal surface. And in fact, the theorem is the following. In fact, you don't have exactly one minimal surface. In fact, you have a finite collection of disjoint minimal surfaces in M. So I will denote this by S1, SP, and some integers N1, NP, so in N, such that W of M is the sum for I from 1 to P of Ni times the area of Si. Okay. And here it's important to mention that these surfaces are smooth objects. Sorry? W lambda, yes. Sorry. These surfaces are smooth. There is no more P, things like that. But the thing is that you do not construct any sweep out at the end. You just construct some minimal surfaces.
Yes, but that's the maximum of the in for the sweep out?
Sorry?
Geometrically.
They should appear as the maximal leaf of some sweep out. But it's not true in general. It's not true in general. It's not sure that you have also a sweep out that comes for free in some sense with this result. But the idea is really to construct minimal surfaces. And this theorem tells you, okay, you have minimal surfaces there because this quantity is non-vanishing, so you have to have something on the other side. Okay, so what you see at the end is that this quantity, this singular value, is in fact, in some sense, the area of some kind of something which is a generalized minimal surface, which is a collection of minimal surfaces with some multiplicity. So you have this. So here I mentioned this result. It's when M is of dimension 3. If you want to have a similar result for higher dimension, you have it. It's in the work of Almgren and Pitts. But if the dimension is too large, in fact, if the dimension is larger than 8, then maybe you don't have the smoothness here in the theorem. It disappears. It could disappear, in fact. No, it could be more complicated. In fact, you have a subset of codimension n-7 of singularity. You could have. Okay.
In the case of the example,
yeah.
There may be Ni bigger than 1.
Good question. Is it possible to have Ni larger than 1? Is it possible to say...
You get a lot of roll down.
It's not clear at all because I'm not so sure to understand the question. But the thing is that maybe you can turn a lot of times around the surface M, but the maximal value is just periodic in that case. So you just have one maximal value that could be given only by one surface. Maybe I'm not so sure to understand the question, but I have something in mind which is not maybe yes.
With some geometry such that it has a minimal surface only and say equators.
Yes.
But if you work a lot of time, you shall get that equator a lot of time.
No, in fact, the thing is that you can change something there, but you will see is that maybe I can put here not m, but some multiple of m. Not so sure to be clear what I mean by this. A priori, you don't change this value when you do this. Maybe you can decrease the value, but it's not clear at all. Is there some example where you decrease the value because you turn twice around the whole manifold? It's not clear. But it's a big issue now in the theory to understand exactly what kind of surface you can recover by this theorem. Exactly what can you say about this? You have a deep result in this direction very recently, and you can say something now. You know a bit more about this. But maybe you could have several surfaces there, not only one. The question about the multiplicity is more complicated in general. For example, I say nothing about the fact that the surfaces there are orientable or not. Maybe they are only one-sided or two-sided, and the two possibilities can occur. But the thing is that if the surface is one-sided, then here you have an even number that appear, like yesterday in the theorem. Okay. So I don't know if I have other things to say about this, but if you in order to know if you really understand what happened and what is the whole construction there, let's try to do one example. So you look at the unit 3 sphere. So with the Euclidean metric. So what is this value there? In fact, I have to be a bit more precise about the choice of the homotopy class I want to consider, of course, even if it's not clear that this choice is really important. And what are the Ni, the Si that appear there? So what is the basic sweep out you can consider there is just to apply the example which is there and look at F. So this is contained into R4. And you look at the function F. So in order to be between 0 and 1, which is you look at the fourth coordinates, x4, and you add 1 and you divide by 2. So on the sphere, the minimal point is when x4 is equal to -1, so you get 0. The maximal one is when x4 is equal to 1, so you get 1. And the picture is exactly the following. So this is your S3. And what are the level sets? They are just parallels along the sphere. So you have a sweep out, which is just gamma sub t, is the set of points such that x4 is equal to 2t minus 1. So you have a sweep out like this. So let's apply all the whole machinery with this. So first, what is the value of f of gamma sub t for that particular sweep out? F of gamma sub t, t between 0 and 1. In fact, what you see, so you compute the area of the parallels of this surface, this manifold. and the largest one is just given by the equator. So what you get is the area of S2. Okay, the Euclidean S2. Okay. So as a conclusion, you know that this value, which is just the infimum of all this quantity, is less than the area of S2. Okay. So I apply the theorem, and what I see is that in fact this quantity can be written as the sum of some integer multiple of area of minimal surfaces. So W of lambda is just the sum from I from 1 to P of Ni, the area of Si. Okay. But there was an exercise before, which was exercise prove that any minimal surface in the unit 3 sphere has area at least the area of the equator, so at least the area of the unit 2 sphere. It was a question as an exercise. I don't know if you have found some idea to prove this. But it tells me, okay, this sum is larger at least than the area of S2. So W of lambda is larger than the area of S2. So W of lambda is exactly the area of S2. So this sweep out there is in fact optimal for the problem. And it tells me that the surface you get here is just S2 by this construction. So the theorem constructs the equator of S3. So it's not really interesting in that case to use this whole machinery to produce the equator of S3 as a minimal surface in the unit 3 sphere, but it's only a basic example we can say something really precise, and in fact there is no so many cases where you can do this. As an example, another example, and an exercise. Exercise. What is the surface produced by this theorem, by the theorem, when M is RP3? And let's think about this. It's not an easy question. Okay. So I have still 20 minutes to the end. So I will let this on one side, and I will go to try to understand minimal surfaces, minimal hypersurfaces in the unit sphere. And you will see today, but more tomorrow, that my interest is trying to understand what is the index of a minimal surface inside the unit sphere. Why I'm so interested by the index? Because of this theorem. So this theorem is produced by applying some Morse technique, and there is a classical result in Morse theory for manifold, a function on a manifold, try to find the critical point of this is that when you do such a procedure there, so you look at a loop, and you look at the maximum of the function along the loop, and you try to minimize. And you find a critical point. And there is a theorem that tells you, okay, that critical point has index, Morse index, 0 or 1. And in general, it's equal to 1. And the question is the same there. What is the index as a minimal surface of the surfaces produced by this theorem? And in fact, this idea of the Morse theory that I exposed there, I do it only for sweep out defined by this. So for family parameterized by only one parameter. So a priori there, I get something which has index 0 or 1. But if I do this with higher in the number of parameters, maybe I can find something there. And there is also a theorem that tells me, okay, you can do this. And you find also some minimal guy there. But the index has to be larger. It's less than the number of parameters, a priori. There is no so powerful theorem for the moment in that direction. There is some version of this, but not the expected one. Okay. So I want to look at the index of some minimal hypersurfaces in the unit sphere. Okay. So what is the first question I want to look at? So index of minimal hypersurface in, so say, Sn plus 1. So the unit sphere in Rn plus 2. And the theorem maybe I will try to prove today, but I'm not so sure to have the time to do this. It's following a result. I don't know exactly to who I can address there, because it appears several times in the literature. It's not very identified who is the guy who proved this the first time. So, let sigma be a two-sided minimal hypersurface of Sn plus 1. Then the index of sigma is at least 1. And in fact, we have already seen this result. I will explain why. And the index of sigma is equal to 1. This implies that sigma is an equator. And if the index of sigma is larger than 1, then the index of sigma is at least n plus 3. So there is a gap in the possibilities of index for minimal hypersurfaces in the unit sphere. So why this is already known for us? It's because the thing, if the index is not at least 1, it's 0. So the surface is stable. But the unit spheres there has positive Ricci, and we have seen that there is no stable minimal hypersurface when the Ricci curvature is positive. So we know that the index can't be equal to 0. Okay. So in order to prove this, I need some computation not so hard computation, but let's do one thing. So I look at sigma sub n, sigma n inside the unit sphere. Okay, and I see this inside the Euclidean space of dimension n plus 2. So if you take a point on sigma, it gives me n plus 2 coordinates there. So I have, in some sense, n plus 2 coordinate functions which are well defined on sigma, and I'm interested in computing the Hessian of this. So the thing is that, so it's a computation, in fact. So you let E be a vector in Rn plus 1, x inside sigma, and you look at the function ue of x is just the scalar product. Yes, sorry? N plus 2. The sphere of dimension n plus 1 is inside the... Oh! Thank you. So you look at, in fact, in some sense, the coordinate of the point x in the direction E. And in fact, you have also another thing, which is the n inside Rn plus 2, which is the unit normal to sigma inside the sphere of dimension n plus 1. So it's still a function in Rn plus 2. So you still have n plus 2 functions which are well defined on sigma. And I will denote these by nu e of x is just n of x scalar e, scalar product of these two. And here the computation I want to make is to compute the Laplacian of this. So basically, if I look at u, let u and v be tangent vector to sigma, and look at the computation of the derivative with respect to v of the function ue. So let me recall that d there is the connection, in fact just the differentiation inside this Euclidean space. Okay? So you want to compute this. So it's quite easy. It's just the scalar product of v with e. Okay. Let's do a second computation, which is the derivative of w with respect to the, in fact, it's not this, it's w times ve, the differentiation with respect to w of ve. What is this? So it's just dw v e. E is a constant vector, so there is no problem with this. Okay. So now let's do some computation about this. So this is the differentiation of v with respect to w. Okay? So at the point x, there is a part of this term which is orthogonal to the unit spheres there. And this quantity is given by what? It's given by the second fundamental form of the sphere inside Rn plus 2. And the sphere, it's well known, so this quantity is just minus the scalar product of v with w times x. Then after, you have the tangential part of this to the unit sphere. And what is this? It's the derivative, it's the connection nabla bar w v e. And I recall that I use nabla bar in order to denote the connection inside the unit sphere, inside the ambient space I look at. Okay? and I play exactly the same game, which is this differentiation there. There is a part which is orthogonal to sigma and a part which is tangent to sigma. So what is this? So the u VE. So there is minus V W X plus something which is, if I use A to denote the shape operator of my hypersurface inside the sphere, which is A of so A of V. In fact, it's symmetric, so no way. N plus nabla W of V. You take the scalar product of E. And here it's just the connection inside sigma. Okay, so from this what I get is the following thing, is that the Hessian of UE applied to V and W is just, so this quantity minus V W multiplied by X, the scalar product of X with E, so it's UE, plus another term, which is this quantity, so it's A of V W, the scalar product of N with E, so it's nu E. So you have a computation of the Hessian. In fact, when you look at the Hessian, this term does not count into the computation. In fact, you have to remove it at the end of the computation of the Hessian, so there's nothing to stay. Okay, so you have this. And the thing is that you can play exactly the same game when you compute this in order to compute the Laplacian of nu E. So you play the same game. You see that this quantity can be decomposed as a part which is orthogonal to the unit sphere, which is, let's do the computation there once, which is just V minus V scalar n x plus nabla bar Vn. But V and n, V is tangent to sigma, n is normal to sigma, so this is equal to 0. And you have then after A, V, so you have this quantity, and this is just minus A of V. The shape operator is computed by this quantity. So you have this. You can also do the computation for dW dV of n. So you differentiate this, and what you get at the end is minus the scalar product of W with A of V X, and maybe there is a plus minus A of V A of W scalar n minus this thing. Okay, so you have this expression, and the thing is that you want to compute the Laplacian of nu E, so in some sense you want to take the trace of this. And I will give you the result. So what is the Laplacian of nu E? So you take the trace of this computation, and you compute the scalar product with E. So first here you see the trace of A. The hypersurface is minimal, so the trace of A is equal to 0. Okay. You have a second term which is there, and what you see that appear is in fact the square norm of A when you take the trace. So you have a first term which is minus the norm square of A mu E, since you have n and you take the scalar product with E at the end. And you have this expression there. And the thing is that what you can prove is that this last term gives you 0. And the thing is that the fact that this gives you 0, so it's just a computation, but you have to use the Kodadzi equation at once in order to prove that you can commute some quantity in the computation and prove that at the end what you see is just the differentiation of the mean curvature vector, and since it's 0, you get 0 at the end. So you have this. So what is the consequence of this? And what is the consequence of that computation there? Look at the Jacobi operator, which is the Laplacian on sigma. So here it's the Laplacian on sigma, plus Ricci in the normal direction, plus A squared. So this is the Jacobi operator. But here I'm on the sphere, so Ricci is exactly n. So in fact what I get is this. So what I see also is that L of nu E, so it's the Laplacian of nu E plus A square of nu E, but because of this it gives you 0, plus it's equal to n nu E. So n is an eigenvalue of the Jacobi operator. And in fact, it's not exactly n, because you have to put a sign in order to consider the stability operator. And what you see is that minus n is inside the spectrum of minus L. So the thing now, you want to compute the index. So you have to what you want is to compute the number of negative eigenvalue you have for minus n. So you see that minus n is at least one eigenvalue. But in fact, the function I have there, it's nu E. So it's for some vector E. But I can change the vector. And I find a new function, which is still an eigenfunction for minus L, with the eigenvalue minus n. So I have some multiplicity on it. So what you see is that it's the following. So you take F1, E1, En plus 2, an orthonormal basis of Rn plus 2. And the question is maybe nu E1, nu E2, nu En plus 2 are independent. So maybe nu E1, nu E2, nu En plus 2 are independent eigenfunctions. So what I see at least n plus 2 eigenvalues, negative eigenvalues for the Jacobi operator. Okay. But one thing is that the first eigenvalue for the operator is non-degenerate. So in that case, it can't be minus n. So there is another one which is less than minus n. So since the first eigenvalue is non-degenerate, there is another one which is less than minus n. So if I compute, I get n plus 2 times minus n plus one another. So I get n plus 3 negative eigenvalues. So in that case, the index of sigma is at least n plus 3. The remaining case is to say, okay, but I assume there, so maybe that these eigenfunctions are independent, but a priori it's not always the case. Maybe you have some relation between them. So if not, there is a relation between these two, these n plus 2 eigenfunctions. So there is, in fact, E in Rn plus 2, which is not equal to 0, such that mu E is the constant function 0 on sigma. Okay. Okay, I have this. So it tells me that the vector E is orthogonal to the unit normal at any points on sigma. But it tells me another thing. Is that where is the computation? Okay, look at the expression which is there on the second line. So the Hessian of the function UE is equal to minus UE times the metric on sigma. So maybe UE is the constant function equal to 0. Okay, it's a possibility. But it tells me that any point on the surface on sigma is orthogonal to E. So it implies that the hypersurface is a parallel of the sphere, and the only parallel which is minimal is the equator. So you get the equator. And maybe UE is not 0 everywhere. But in fact, we have seen in the lectures of Thomas that when you have this, you can apply the theorem of Obata that tells you, okay, if you have some estimate on the Hessian, exactly this, then you can say something. And in that case, you have to apply Obata theorem. And this proves that sigma is isometric to the unit sphere of dimension n. So the last point of the proof, and I will let this, we'll stop there, it's not very hard to prove, is that if you have a minimal sphere, a minimal hypersphere like this, inside the sphere of dimension n plus 1, which is moreover isometric to this, but it's just an internal isometry. It's not a, you don't know how sigma is embedded inside the sphere of dimension n plus 1, then it has to be the equator. Then sigma is an equator. Okay. So this finishes the proof of the theorem, and I will stop there. Thank you for your attention.